about the containments problem between power of ideals. Okay, so Professor Taiha.
Thank you so much. So in my last lecture, I've mentioned about the problems of when the Hilbert functions is maximal. So for this lecture, I'm going to focus on a slightly different questions. That is when the Hilbert functions is different from the Hilbert function of the polynomial ring itself. So the title for this lecture is going to be Initial Degrees, Chudnovsky and Demai's Conjectures. So these are going to be discussed in this lecture. So let me recall. So here I'm going to basically fix the set of point P1 up to PS. And this is going to be inside my Pn. And again, I'm working over the complex numbers. I'm going to fix an integer, a positive integers, and I'm going to consider the collection of fed points with supports in X and the same multiplicity M. So the question is that we're going to discuss in this lecture is when or for which value D, when is I of Y at degree D not the same as 0. So this is really the same as saying that for which value D there does exist homogeneous polynomial of degree D in R. Oh, and once again, R is going to be coordinate ring of the given projective space that vanish at the point in X with multiplicity at least M. So that's the question that we are interested in. So for this, I'm going to give a, maybe I'm going to focus on, maybe I'm going to look at sections 2.1. I'm going to focus on initial degree. So here I'm going to start with a definition that captures what we are interested in this question. So for a homogeneous ideal I inside our polynomial ring, of course, we let alpha of I denote the least generating degree. Of I. And that is the same as saying that alpha of I is going to be mean of all degree D, such that if you look at the degree D component of I, this is not 0. So this is going to be what we are interested in, and primary objects for us is going to be alpha of I of Y, right? So this is the questions, and now we have rephrased that question in terms of finding this invariance alpha associated to I of y, and as we have seen before, I of y is just I of x to the symbolic power n. So here we are looking at the initial degrees of a symbolic powers of the defining ideal of a set of points. So toward this problems, or toward this question, there are a number of famous conjecture. I'm going to start the first one. I'm going to state the first one. Actually, I'm going to state a few of them. So this is the famous Nagata conjecture. So Nagata conjectures that if you have a set of at least 10 general points in P2, and once again, I still haven't explained what general means. I promise I will come back to this. Then alpha of the symbolic powers, the M symbolic power of its defining ideal is at least M times the square root of S for all M being positive integers. In fact, it can be proved that this equality actually holds. So Nagata's conjecture basically predict precisely what this no, sorry, that's not true. I'm sorry, that can't be true because this the left hand side has to be an integer. Sorry for that. And so Nagata's conjecture is for P2, and is still very wide open. And there's a conjecture that generalizes Nagata's conjecture. This is by Yorobino. And Yorobino basically say, so again here, you see that Nagata conjecture that this inequality should hold with some exceptional cases, meaning S cannot be, if you take S to be less than 10, there could be situation where this is not true. So Yorobino generalized this conjecture to any Pn, and once again, he would have a collection of exceptional cases. So let X be a set of S general point in Pn, where, so the exceptional cases for him would be S is going to be at least max between n plus 5 and 2 to the end. And he also wants the pair S and N not to be the same as the pair 7, 2, pair X 2, 9, 3, or 14 and 4. So those are the exceptional cases. Then he predicts that alpha of Ix, again, to the symbolic power M, is at least M times the nth root of S, for all M being a positive integer. So both of these conjecture, of course, are very wide open. There are a lot of works regarding Nagata's conjecture, and even in P2, this has proved to be a very difficult conjecture. And notice that these two conjectures are for set of general points, right, or general set of points. There's also conjecture for any set of points, and so that's the next conjecture that I'm going to state. So maybe I'll state the next conjecture together. This is 2.4. So here I'm going to let X be any set of S point in Pn. Right? Then Chudnovsky in early 80s, around 1981, conjectured that alpha, maybe write this, all right, for all positive integer m, we have alpha of the m symbolic power of the defining ideal of X divided by m. This is bounded below by alpha of I of X itself plus n minus 1 over n. And then a few years later, this conjecture was generalized by Demai, and he conjectured that for all m and t being positive integers, we have the left-hand side is still the same, alpha of I, or the m symbolic powers of Ix divided by m. This is at least, on the right-hand side now, he allows not just to take alpha of Ix, but again, the symbolic t powers of Ix plus n minus 1. And denominator is now going to be changed to t plus n minus 1. So unlike the case for Nagata or Yorobino's conjectures, where they actually predict the values of alpha or the values of the Gauss-Schmidt constant, as I will explain shortly, this conjecture, Chudnovsky and Demai give a lower bound for that invariance. Okay. Now, of course, one can see very easily that Demai implies Chudnovsky.
Professor Taiha, what is n here?
You mean this big N?
Yes, big N. Okay,
Oh,
this is defined here.
Yeah, it's just any number. It's just the dimension of the ambient space.
And it is also same as in conjecture 2.4?
Yes, yes. Okay. So this is also N, right? So you take a set of points inside the ambient space of N dimensional, then that's just the dimension of the projective space.
Okay, thank you.
That's a very good question, because later on when we try to generalize this conjecture to beyond set of points, then in fact you no longer take this to be the dimension of the ambient space anymore, but in fact you're going to take that to be the big height of the ideal or the defining ideals. So we'll see that hopefully in my last lecture. So
at this moment, is there any relation between S and N?
No. So at this moment, N is just any given dimension. You are sitting inside a projective n-dimensional space. For example, you're in P2, then n is 2. You're in P3, then n is 3. You're in P4, then n is 4, etc. S is just the number of points. You can take any number of points inside any projective space.
Okay. Okay. Thank you. Thank you.
Yes. Okay. So for the let me maybe one minute. So these two conjectures are going to be the focus of my lectures, my third and my fourth lectures. And in the end, I'm hoping to present a proof of this conjecture for a general set of points using containments of ideals. So containments of ideals is very algebraic notions and techniques. And I'm going to hopefully be able to show that this can be applied to this a little bit more geometric problems. So these two conjecture can be rephrased in terms of another invariance associated to an ideal or the defining ideal of a set of points. And so I'm going to move on to define that invariance is called the Wahrschmidt constant. So the Wahrschmidt constant is defined for any homogeneous ideal, right? So let me write down the Wahrschmidt of a homogeneous ideal. Again, in my polynomial ring R that I'm already fixing, is defined to be so the Wahrschmidt constant is going to be defined denoted by alpha hat, and alpha hat of I is going to be just the lim as m goes to infinity of the quotient similar to the quotient that you see in Chudnovsky and Demai's conjecture. So look at alpha, which is the list or the initial degree of the m symbolic power of I, and then divided by m and take the limit as m goes to infinity. Now, of course, the first question would arise, is this well-defined? Right? So just to give you some fun, I'm going to give you an exercise. So maybe I'll include this number. This is 2 point. Well, maybe I don't have the number. Maybe let me just keep track of my number. So this is 2.6 somewhere. And that is 7, because I might need to refer back to this number later on. Show that this is a well-defined invariance. And in fact, instead of taking a limit, you can just take the infimum of this quotient. Of course, m here is inside the positive integers. So let's look at some examples. Now, it's very easy to see that alpha hat is no more than alpha, just because, again, if you know that this is true, then when you take m to be 1, this is just alpha of I divided by m, right? Provided we talk about radical ideals, okay? And another way to see this is, again, this is because we know that I to the m is contained in I to the symbolic powers, right? So instead of having I to the m here, because of this containments, it implies that the initial degree of this guy is at least the initial degree here. So the initial degree here is at most the initial degree here, which is m times the initial degree of I. So when you divide by m, you get rid of that m, and what you have left is the initial degree of I. Okay? So and so this is easy, and particularly if you have the equality for all m, and this equality is an equality that a lot that algebraists have been studying a lot lately. Then we have the equality between alpha of I and its Wahrschmidt constants. So that's one example. The next example is this. Actually, this is a very recent result of many people. Fanik, maybe I'll use et al. And this is a result in 2017, so it's quite recent. And they basically determined alpha hat of the defining ideals of Ix, of a set of point X, is determined when the number of points in X is at most 8. Right, so you have fewer than 8 points, then the Wahrschmidt constant is known, so one can check all kinds of inequalities. However, if you have more than 9 points, things get a lot more complicated. And of course, problem computing with the Wahrschmidt constant becomes very difficult. Another thing that starts from Nagata's work. So this is when he proved, this is when he made the conjecture. And of course, this is in his work in giving a counterexample to Hilbert Fortin's problem. He basically, maybe I should say that Nagata do this for n equal to 2, meaning points in P2, and generalized for all n by others. I might not remember precisely who's the first one. But the method of generalization is quite straightforward. So it's proof that if X is a set of, so the number of point now is a power, n power of some integers, general point. In Pn, right? So there's now, this is where there's a relationship between the number of points and the dimension of the ambient space. Then the Wahrschmidt constant of Ix is exactly k. And if you notice, this is the same as the n to the s, right? Now, if you look back at Yerovino's conjecture, this is the condition if you divide it by m, right? So if you divide by m, you get rid of m. On the right-hand side, you have exactly the n to the s. And so because of that, and the limit exists, so already from this conjecture, or this conjecture is equivalent to say that the Wahrschmidt constants of Ix is at least the n to the s. In fact, the other inequality is already known. So the conjecture is equivalent, is in fact equivalent to saying that the Wahrschmidt constant of Ix is exactly the n to the s. Okay, and so this established that conjecture, or Nagata and Yerovino's conjecture, in the case where the number of points is exactly k to the n. So it's the n power of some positive numbers. Generally, of course, it's very, very open. There's a bound. This is known before Chudnovsky and Limai. It's by Skoda in 1977, where he proved that the Wahrschmidt constants of a set of points is always bounded below by alpha of x, of Ix divided by n. So this, if you look at this, you see that it's quite close to what the conjecture, or what Chudnovsky's conjecture is, right? Chudnovsky's conjecture basically say, well, instead of having just alpha by x over n, you can even increase the numerator by n minus 1, right? So let me rephrase, just to keep things in context, let me rephrase Nagata, Chudnovsky, and Limai's conjecture in terms of of alpha hat. Okay, so Nagata and Urobino. Urobino also call this Nagata's conjecture. So generally people call it Nagata's conjecture. Let X be a set of S general point in Pn, then the Wahrschmidt constants of Ix is the same as the nth root of S. And now this is where I can say that this directions is known to hold, right? So one need to prove the bigger than or equal to inequalities. And for Chudnovsky and Dimai, so let X be any set of S point in Pn, Chudnovsky basically says that alpha hat of Ix, which is the Wahrschmidt constant, is at least alpha of Ix plus n minus 1 over n, and Dimai say that alpha hat of Ix is at least alpha of Ix to the symbolic t power plus n minus 1 over t plus n minus 1 for any positive integer t. So these are the conjecture related to the question that we stated at the beginning of this lecture. The focus for me would be the last two conjectures, Chudnovsky and Dimai's conjecture. I'm not going to talk about Nagata's conjecture from now. So what is known, or what has been known with these two conjecture? Known cases. So Chudnovsky's conjecture is known to hold in the following cases. Let me highlight this. Any set of point in P2 so regardless of number of point, excuse me, regardless of the number of points, this is proved by Chudnovsky himself, where he generalized what Skoda has proved before, and because of this, he made the conjecture. So he proved for points in P2, and he made the conjecture for any point. His proof actually used a method in complex analysis. A general or set of general point, a general set of point. So I usually use interchangeably set of general point or general set of points. They mean the same thing for me. In P3, this is proved by Dumitsky in 2015, so it's not too long ago. a set of n plus 1. So here is another case where the number of points is related to the dimensions. Points in generic positions. So let me just put out a terminology, and then I will explain what that means. So point in generic position is very much the same as saying that it has the maximal Hilbert functions. So it's nothing special here. It's just different people use different terminology in PN. Now, if you look at this, you notice that if you take n plus 1 points in generic positions in PN, you can basically think of this point as being the coordinate point. It's like, if you're looking at the XY plane, you look at the point 0, 1, and 1, 0. If you're looking at three-dimensional space, you're looking at all the coordinate points. So it's the same thing here. This is again by Dubnisky. In the same paper, 2015. A set of a binomial coefficient number point forming a star configuration in PN. So let me, instead of explaining exactly what star configuration means, I'm going to just draw an example for you. So this is a star configuration. I mean, you have five lines, or maybe even 4, that's fine. So where they intersect nicely, meaning there's no 3 lines that intersect at the same point. And then you're looking at the intersection point. And so if you have 3 lines, then you'd have 3 points. If you have 4 lines, then you get 6 points. If you have 5 lines, then you get 10 points. And if you look at those numbers a little bit closely, you realize that 3, 6, 10, those are the same as the number of the Hilbert function of the polynomial ring in 3 variables, right? So those are of the form n plus d choose n, right? Or d plus 2 choose 2 in the case of P2. Last lecture, we look at an example where you have 6 points, right? And we explain the Hilbert functions. So that's why it's called binomial coefficient number, because it's of the form d plus 2 choose 2, or n plus d choose n. And they represent the Hilbert function of the polynomial ring itself. So that's what it means by star configurations. And the binomial coefficient is just exactly what is explained. So this is by, so this is done by Jiromita, Auburn, and Liore. I believe in 2013, and probably it was already included in Bokchi and Auburn's work, maybe not explicitly, in 2010. Okay, so that's the next case. And then we have just any set of points lying on a quadrix. And this is a result of Fowley, Montero, and C in 2018. So the best way to visualize this is if you look at P1 cross P1 sitting in P3. So that's going to be a variety defined by a quadrix by a degree 2 equation. And if you look at a bunch of points on that curve, then it's going to satisfy Chernovsky's conjecture. At least 2 to the n very general point in Pn. So here again, you have a relationship between the points and the dimension of the ambient space. And we have a new terminology, very general set of points, which I'm going to go back, return to and discuss in more detail shortly. This is a result by Durmitsky and Tataj Gazinska in 2017. And any very general set of point in Pn. So this is a generalization, or not generalization, but an extension of the previous results. We're getting rid of the condition that you have to have many points. This is by Fowley, Montero, and C. And the methods used in these papers are very different. The first paper used a more geometric method, actually making use of Nagata's conjecture, what is known about Nagata's conjecture. And the second one is more algebraic method, which is what we're going to talk about soon, at least in the last 2 lectures. So we also work on this conjecture, and our result is a set of at least 4 to the n general point in Pn. Or you can improve 4 to the n by 3 to the n if n is at least 4. And you can also improve 2 to 2 to the n if n is at least 9. So here is general set of point, right? So the difference between these 2 results is that here you have a requirement of of the point being very general. Here the requirement is that the point is just general. This is the recent results of Bissuit, Griffo, myself, and Nguyen. So we proved this last year, and it's still it's going to appear in the transaction of the AMS maybe next year. Okay, so and then the next question, the next natural question. Well, here we have a bound for the number of points, just like here they have a bound for the number of points. What happened to smaller number of points? So there's a recent results by Bissuit. Maybe I should write the results first. That's it's true for n equal to 3, or maybe 3 is already known, 4, 5, 6. It's true for n equal to 7 and 8. And you have 2 to the n less than or equal to s less than or equal to 3 to the n. So they can drop the number of points slightly. Or if n is at least 7 and n plus 4 less than or equal to s less than or equal to n plus 2 choose 2 or choose n. And the points are general point. So I should also point out that in this case, for example, when S is less than n plus 4 is already known to be true. So what they do is they take care of the next batch of numbers. So those are the, for small point, this is a recent result by Bisui and Nguyen in recently. So both of these are my Bisui is my former PhD students, and Nguyen is my current PhD student. Okay, so that's what is known for Chudnovsky. Limai, unfortunately, is not very well studied as Chudnovsky was. So, so the first situation for Limai is known when you have point in P2, right? So point in P2. So any set of points, and this is by Esno and Vivek. In 1983, so it's a long time ago. And then it's known for at least t plus 1 to the power n for fixed t, fixed number t, and that fixed number t is inside the conjecture, a very general set of points. In Pn, and once again, here you see the condition being very general set of point, and this is the recent results of Malara, Schamberg, and Spahn in 2018, and it's slightly generalized by Chang and Zhou in 2020. And the next results is a set of at least 2t plus 2, so it's a little bit bigger than this, to the power n, again for a fixed t, general point in Pn. So here, the requirement is that the points are general, and this is results by Bisui and Guifort, myself and Nguyen, and this appear in 2022 of the Journal of Pure and Applied Algebra. So I've mentioned more than once the notion of very general and general set of points, and I'm going to try to explain to you what those means. Very general, a point. Now, technically, if you want to talk about general set of point or very general set of point, one has to look at the varieties parameterize a set of point or zero-dimensional subscheme of given length. So you have to go to the Chow variety or the Hilbert scheme of point. But first, there's a much easier way to view general and very general set of point, and that's what I'm going to try to explain to you. So once again, we fix a set of point P1 up to PS inside PNs, and let me just write PNC here. And PI has coordinates AI0 up to AIN. So I can actually view this set of point as a matrix, right? So I can view as a matrix where I put A, and I just put all these coordinates. I get A10, A11 up to A1 end, and AS0, AS1 up to AS end. So this is going to be a S by n+1 matrix, and I can view this as a point inside my S times n+1 dimensional affine space. Right? So I can view a collection of points as a matrix, more or less. Of course, this is not a precise one-to-one correspondence. Of course, for different set of for different matrices, you might have the same set of point. Remember that a projective point is determined if you a projective point doesn't change if you multiply every coordinates by the same constants, right? So you can have different matrices with giving you the same set of point. So now what I'm going to do is I'm going to look at a collection of new indeterminates or new variables. So let Z be Zij's, and I'm going to look at this as in terms of matrix to fit with what I have seen up here. So this is going to be I running from 1 to S and J running from 0 to N, be a collection of S times, again, n+1 new indeterminates or new variables. And then I'm going to extend the complex number by this new variable. So let C of Z be the transcendental extensions of C by Zij. Right. Excuse me. And so basically I can think about replacing each number here, this is complex numbers, by a new variable. So each point here is now, I can also do the same. I can replace each number here by a new variable. Okay, so I'm going to let Pi, and I specify that to be at Z, to be the point Zi0 up to Zin, and this is the point inside the n-dimensional projective space, no longer over C, but over this field extension. Right? So I have a field extension, and inside this field extension, of course, the Z are considered as numbers. I can look at the n-dimensional projective space over this field extension. So then, then I can form the collections of points. So let XZ just be the collection of P1Z, PSZ. Now, what you can see is that it really doesn't matter what P1 of 2PS that I start with. When I add Z in, I get the same guy because it's all in terms of Z ij, right? So it doesn't matter what Aij that I start with, the Z are always fixed. So going from X to XZ, doesn't matter what X I have, there's only one unique XZ. So this is the one set, right? So I call this the set of S generic point. Right, so this is generic, not general. Generic, and of course, it's sitting inside my, again, n-dimensional projective space with over the field extension. So this is one process. I can replace the A by the Z, but I can also go backward. I replace the Z by the A, right? So if I'm given this guy, and now I can, instead of looking at the Z, I can replace the A in. Then given one specific generic set of point for different A, I get different guy, different set of point down stack. So I'm going to let XA denote what is obtained from XZ by replacing Z with A. Now, as I said before, in these replacements, when I replace Z with an A and I get a matrix, it doesn't necessarily give me a set of distinct points. It could happen that two rows are somehow proportional and they give me the same point, right? So in this replacements, I no longer necessarily obtain a set of S distinct point in Pn. However, if I avoid all this trivial condition, for example, if I avoid all the condition that one row is a multiple of the next, then I would have a set of distinct point. Right? So in fact, the fact is that there exists an open subset let me denote by a W0 inside my parameter space, such that for all A inside this open subset, this guy now is a set of S distinct point in Pn. Okay, so this is this process is called specialization, right? So I specialize the generic set of point to get a set of point down stack in Pn, and this is now over C. Right? So going XZ, you substitute Z by A, you get XA. This process is called specialization. And I'm going to talk about specialization in more detail later. So what does it help us in understanding what it means by generic or by general or very general set of points? So this is the definitions. In fact, it's the result proved by Fowley, Montero, and C, is that if you look at this process, you can define very general and general set of point in the same way that if you were looking at the Hilbert scheme or the Chow variety. So a property P is set to hold for a general set of point in Pn, right? So general set of point or just set of general point. If there exists an open dense, I should say that this is open and dense, right? So open dense. Open dense subset U of my parameter space, or exactly this W0 set, such that, and this is of course inside my parameter space, such that P holds for any specialized set of points if you take A to be in this open dense subset. And a property P is set to hold for a very general set of points in Pn, very general, if there exist infinitely many open dense subsets All right, U and these are still contained in W in 0 inside the parameter space for n's running from 1 to infinity, okay? Such that P holds for any specialized set of point XA for all A inside the intersection of this U end. So, of course, theoretically, if you look at an infinite collections of open subsets, you don't quite really know what this intersection should be, right? It could even be a closed subset, okay? So going from a statement, proving a statement for very general set of point to general set of point is quite a difficult problem. It's like going from having infinite intersection to a finite intersection, or in fact to just one subset. So you have to find, here you have infinitely many subsets satisfying certain conditions so that when you take the intersection, you get property P. Here you have to find one subset that holds for infinitely many conditions, right? So that is the difference between the two. So I hope that I have been able to show you the difference between very general and general set of points. In my next two lectures, I'm going to talk about containments of powers of ideals. So maybe I will start containment of power of ideals maybe for a few minutes, and then hopefully be able to explain to you how containments of powers of ideal can be used to prove Tunovsky and Demey's conjecture for a general set of points, maybe sufficiently many points, right? So containments.
Yes, can you hear?
Of ideals. Or maybe let me see. I see a few.
Professor Han, there
Yes.
are a few questions.
Yeah, a few questions in the
probably,
chat.
yeah. Probably there are a few in the chat, and probably you need to shed more light on the specialization, I think.
Yes. So maybe it's good time for me to stop and just try to address the questions. So the first question I saw was, is there an analog for maximal Hilbert function in terms of commutative algebra? Well, the notion of maximal Hilbert function is a commutative algebra notion, right? It's basically say if your Hilbert function is maximal possible, right? So you have Hilbert function less than or equal to some number, and if it's attain that number, then it's maximal. So it is, for me, I consider that as a commutative algebra conditions. The second one is restriction on S and N is only for conjecture 2-3, conjecture 2-4 as well. So 2-3. Yeah, so both of I guess you're talking about Tunovsky and Demey's conjecture. The restriction on S and N of known results separately for either of the conjecture. For example, you know some Tunovsky's conjecture holds for some cases where you have restriction between S and N, but then you also know Tunovsky conjecture hold for some other cases. Unfortunately, there are a lot more work regarding Tunovsky's conjecture compared to works regarding Demey's conjecture. Much less is known about Demey's conjecture. Any other question?
Yeah, there is one question. What is the relation between the topologies, Zariski topologies, between the PN and the specialization space?
So that's a very good question. So So the topology are both Zariski topology, right? So the closed subsets are still vanishing or the zero set of a bunch of polynomials. However, when you look at the field extension, you're looking at polynomials where your coefficients are allowed to be inside a bigger field, right? So that, of course, add more closed subsets, right? On the other hand, if you restrict it to Pn over C, you're looking at polynomials where your coefficients are just complex numbers. But now, if you move up to the guy upstairs, your polynomials are allowed to have coefficients that involve the new variable z, right? So there's not a clear relationship between closed subsets of the two. That's a very good question.
Yeah, that is something how we are relating this configuration. So this technique is just to see the configuration in affine setup.
No, it's the technique for specialization.
Yeah, exactly.
No, I mean the technique for specialization it's for projective space, right? So all I have been talking about is about variety of projective space. So for example, here, let me see, where is it? Here, right? So I'm looking at I'm thinking of this guy sitting on top of Pn, right? So this guy sitting on top of my Pn here, and so the specialization basically say, well, I take this generic set of points, and that's just one set of points, right? And then I substitute specific values into the variables, right? For different way of values or different collection of values, I have different set of point downstairs. So one set of point here for different substitutions, you get different set of what, or maybe just one point here. For different substitution, you have different point downstairs, right? So the specialization is basically a technique that allow you to say, well, if you can prove that something is true for this generic point, then when you specialize, it's like here, right? As I said before, if you just given values here, you don't necessarily obtain a set of point in Pn. For example, a set of distinct point in Pn. For example, when you substitute the values in, it could happen that the two rows are proportional. Then the 2 points will be the same, right? But you can, by avoiding a finite number of conditions, such conditions, you can actually get a set of distinct points as long as you are in a in an open subset downstairs, right? So what this is saying is that you have a statement that is true. You have a set of distinct points in this bigger space. So you have a set of distinct generic points. When you specialize, you almost always get a set of distinct points downstairs, but you don't always. You almost always, right? So the technique of specialization is you want to prove some statements that hold for almost always. Then instead of working downstairs, you go directly upstairs, where instead of having a lot of set of points, you just have one set of points, and you just work with that very specific set of points, prove whatever you want, and then use the kind of the philosophy that if something is true up here, then it's almost always true down here. That's the meaning of specialization.
How it enforces that there exists such an open subset W0. I was just trying to speculate how this existence.
Oh, you mean here?
Yeah.
So yeah. So this actually is a nice exercise. So you have to see. Okay, so let's say I substitute. So basically, I think of substituting the Z by a matrix here, right? Yeah. And so when I do that, this will give me 1 point. The next row give me another point. The next row give me another point. When would this points be? When would this point be completely distinct? And the condition is that you don't have any two rows that are proportional. right? Two projective points are the same if if one is a multiple of the other one, right? So you just need to avoid the condition. For example, if let's say I put the condition that the determinant of the, not the determinant, the rank of the matrix is maximal, right? So if this matrix, whatever it is, has maximal rank, then it cannot have two rows that are, one is proportional, is a multiple of the other one, right? And so the maximal rank condition would be a condition that gives me a set of distinct points. And so W0 here is the open subset determined by the rank condition. So looking at all S by n+1 matrices with maximal rank. That's an open subset of the collection of all S by n+1 matrices.
That's it. Thank you. Thank you. Maybe there is some other question.
I enable the mic so anybody can speak in the mic.
Maybe some other question from the audience. Oh, yeah.
You can use.
How we can define Welch-Schmidt constant in context of projective varieties?
So the Welch-Schmidt constant is defined for homogeneous ideal, right? So that's why, because the Welch-Schmidt constant is determined by looking at the least generating degrees. So when you talk about least generating degree, you want your ideal to be homogeneous. That's why everything I talk about is in the context of projective variety. Because if you move to R5 variety, then you no longer have the homogeneity, right? So you just take a homogeneous polynomial, homogeneous ideal. You look at its m symbolic powers. That's also a homogeneous ideal. And for homogeneous ideal, that you know that it decomposed into homogeneous pieces, right? You just look at the least degree zero, the least degree piece, the first one that is non-zero, and that is the degree, and you divide it by m, which is the symbolic powers, and then you take the limits, and it's as I put it as an exercise that that limits exists, and that's how you define the Welch-Schmidt constants. Did I understand your question correctly?
In fact, the resurgence and other things will connect automatically with this whole setup.
So I'm not going to talk too much about resurgence number, but because I'm talking about containments, of course, it's going to be very closely related, because resurgence is to measure the non-containment, right? So I'm not directly talking about non-containment. I'm only talking about containments. So yes, there's the connections, but you won't see that connection in my lectures.
And regarding to all these calculations, so is there some combinatorial structure which is linked with it? Some measurable?
I mean, so for me, when I talk about points, I also think of it as combinatorial, but not in the sense that you're saying, like, if matroid and things like that. So yes, so unfortunately, in my lecture, this is as much of combinatorics that you're going to see. Most of what's going to come next are pretty much algebraic, about containment of ideals. Yeah, so initially I was very ambitious. I was hoping to be able to talk about both the geometric and the combinatorial consequences of the containment problems, but unfortunately, I don't think I have enough time. So if anyone is interested, I can give you some references to see how, again, with the same kind of containments that I'm going to talk about, in one hand, one can use those containments to prove or to work on the Chudnovsky and the Myers conjecture. On the other hand, one can look at this containment to, one can use this containment to investigate a number of problems in combinatorics, in particularly in combinatorial optimizations or linear programming problems. So if anyone's interested, I'll be happy to share some references.
Any other questions? There are no questions, so.
Is there any other question from online participants or from IBA Karachi? Okay, if there is no question, so let's thank the speaker.
Thank you so much.
Okay, now it's tea break and now we'll resume at 11.